Okay, so related rates is a pretty challenging topic in calculus, and the first two parts of this are just setting up the geometry of it. Basically, you have an airplane flying across the top line of this right triangle, and it's flying so that we can calculate the change in x, right, which is the top distance, the horizontal distance. That's 390 feet per second, right, and it's positive, which is important to note with related rates because sometimes you have things that are decreasing. Here, x is increasing because you're getting further and further away from the observer. They ask for the equation relating x and y. If it's a right triangle, obviously, we're going to have a Pythagorean theorem. It's just 5,000 squared plus x squared equals y squared. Right? Y squared is your the hypotenuse. So that's all they're asking for in part A. Part B, they want to know the value of x when y is 13,000. So if we plug in 13,000, right, if you like all these zeros, then that's your thing. But this is also a Pythagorean triple of 5, 12, 13 if you multiply each of them by 12. If you do want to solve Pythagorean theorem, you're going to get like 169 million minus 25 million, and x squared would be 144 million. Right, so that when you set x right to the square root, you get 12,000 feet. Okay. So, now the important thing with related rates is that you're going to do implicit differentiation for this original equation, right? So like this equation defines x and y in terms of each other at any given time. And what we're going to end up doing with that is we're going to do the derivative of every term with respect to time, right? So before we finished with dx dx's and dy dx's. Here we'll finish every derivative with dx dt or dy dt, depending on what we have. And the important thing with implicit differentiation is they're asking what is dy dt, right, when these two are true, right? So we're not going to plug those values in until after we do the derivative. We just kind of hold on to those values. What you're going to do is do the derivative of 25 million, which is 0, right? The derivative of any constant, no matter how big it is, will be 0. The x squared term, you're going to do the power rule, it's 2x, right? And then you follow it with a dx dt, right? That's part of the chain rule. And then on the other side, you end up with 2y dy dt, right? And this simplifies nicely. The 2's can go away, right? So we end up with this relationship where dy dt will equal x over y times dx dt, right? Now that we've done our derivative, you can actually plug in the values that are given, right? They say y should equal 13,000. We know from part B that x is equal to 12,000 at that point. So our dy dt is going to be 12,000 over 13,000. And then we're going to multiply by 390, right, which is our value of dx dt. So the thousands can go away. It's 12 over 13, and then we multiply by 390, so we'll end up at, let's see, 30, so 360. And this is dy dt, so it's changing at a rate of 360 feet per second. So even though you're moving horizontally at a speed of 390 feet per second, your hypotenuse is only changing at a rate of 360 feet per second.